Okay, we're going to go a little bit deeper this time into standing waves. And what I want to do is develop the mathematics of it so we can understand how a standing wave is going to operate in certain situations. Now, I keep driving home that standing waves are important. And one of the examples that comes to mind is the Tacoma Narrows Bridge. Probably all of us have seen the video by now that bridge has collapsed. If you haven't, get on YouTube and search Tacoma Narrows Bridge, and you'll quickly find the video. The problem there was that the engineers designing that bridge, they did not account for the fact that winds would be coming in and buffeting that bridge and basically making the bridge begin to vibrate and setting up a standing wave in it. And that, coupled with the fact that the winds were buffeting at what's called the natural frequency of that bridge, that meant that not only did the standing wave get set up, but it kept getting fed energy in a way that made the wave forms amplitude larger and larger and larger. And eventually that energy just tore the bridge apart. So standing waves are important. Structures that are outside, tall buildings, they get buffeted by the wind up, especially at the higher floors. All of this can produce wave phenomena that you've got to be able to account for. So to kind of get us started in that direction, we're going to look at standing waves in a very simple situation, and that is standing waves on a string, okay? Now, it's hard to create a standing wave on a string or a wire or anything like that by just oscillating both ends. That's really hard to get the same amplitudes and the same frequencies and all that together. It's a lot easier to do if you fasten both ends of the string to some sort of boundaries, like say walls, and you use a source that can create oscillations from the outside. Your book is an example of a setup like this. I hope you're reading the book. It's really an important part of the way this class functions and being prepared for our time in lecture or in face-to-face. But this is a picture that comes out of your book, and it shows a setup that can create standing waves. You have a mast that's attached to a wire, and it's all hanging from the ceiling, okay? And you've got an electromagnet on the outside that's able to interact with the electrons inside the atoms of the wire or the string, and the electromagnet varies the direction of magnetic and electric fields, and that causes the string to vibrate back and forth. And you can actually use that to set up a standing wave. Now, here's the thing. Since both ends of this wire or string are fixed, okay, only certain frequencies of oscillation are going to set up a standing wave for this string. And the reason that's the case is that this end always has to be at 0, and this end always has to be at 0. And there are only certain wavelength ways where you can guarantee that there are going to be 0 displacements at the boundaries, okay? So let's take a look at this. What I'm going to do is I'm going to make a setup and just try to simplify the drawing down. Here we have a string, and it's attached to 2 walls, okay? I set up a small coordinate system, and we have x equals 0 down here on the left side, and x is equal to L over here on the right side. Now, think about this. I want to go back to what I just said. If we want to set up a standing wave, then both ends of these strings have to be nodes on the standing wave, right? Because these points, since they're attached to the wall, they can never move. They are fixed at 0. They're at equilibrium at all times. And so that's going to have to be a node, and that's going to have to be a node for whatever standing waves will work within this separation here. Okay? Now, what this means then is that the amplitude function is going to have to be 0 at these 2 points. If we were to calculate the amplitude function at 0, it's going to have to give me 0. And if we calculate the amplitude function out here at L, that's also going to have to give me 0. Okay, so you can see how we're already starting to limit what our A of x can be. It's got to give us specific values at specific places. Now, we call these things boundary conditions. You're going to run into them in calculus. You're going to run into them in your differential equations course. Boundary conditions help us determine what a function must really look like. And so for us, functions aren't just math things. They're actually mathematical ways of understanding what is physically going on in a situation. And so these boundary conditions kind of set the stage for what can play out on the string between these 2 walls. Okay? Now, let's take a look at this amplitude function, and let's consider what it means that the amplitude function out here at L has got to be 0. Now let's write it out in terms of its full equation. A of L's got to be 0. Then what that means is that 2a times the sine of KL has got to be 0. I've just substituted L in for X. So this is my boundary condition expressed mathematically. Now, if this has got to be 0, I can reduce this down. The 2a's divided out, and what I get is that the sine of 2 pi over lambda times L has got to equal 0. What I've done here is I've actually put in the mathematical expression for K. K is 2 pi over lambda. And so the sine of this value in here has got to be 0. Now let me ask you a question. When does the sine function have a value of 0? Well, hopefully you remember from your studies of sine functions, that's going to occur at 0 or pi or 2 pi or 3 pi or 4 pi or any integer multiple of pi, right? So we could write it out as m pi, and m can be 1, 2, 3, 4, and so on, okay? And so what this means is that 2 pi over lambda times L has got to be equal to some multiple of pi. It's got to be equal to 0, pi, 2 pi, 3 pi, 4 pi, or so on. And so if we solve this for lambda, we find out that there are certain wavelengths, lambda sub m, which is equal to 2L over m. The pi's cancel out when I solve. And m is 1, 2, 3, and so on. This right here, and the reason I've put m on here is this is the wavelength that works for each integer multiple of pi. Okay? But these are the wavelengths right here that will actually fit in between these two walls and guarantee that you have a node at this point and a node at this point. Okay? This function will always give you that. And so this is how we calculate the allowed wavelengths. And so we could figure out what those wavelengths are. Let's find lambda 1. So the first wavelength that would fit in here, okay, is actually a wave whose wavelength is twice the length of the string, right? So basically a wave where half the wavelength will fit in here, and we go from one node to the next node, okay? Well, if we put in for lambda 2, well, the second wavelength that will work is a wavelength that's just equal to the length of the string. That would give me a node here, and if we were to kind of sketch it in, we're going to see this in a second. We sketch it in, though, it's going to go from here to here to here, and so we're actually able to fit a full wavelength in. So a wave whose wavelength is equal to the length of the string, that will set up a standing wave. Okay, that's a standing wave that will fit here and give me 0 at both 0 and L. Okay, at those two positions. Lambda 3 would just be 2/3 L. Okay, so a wavelength that's 2/3 the overall length of the string will fit in there and guarantee that we can have a standing wave. Lambda 4 would be half of the length of the string, and so on. But the key is these guarantee that a node will be at both ends of the string. Okay, and it all came out of applying the boundary condition and asking, what does that tell us? Okay, so there's multiple wavelengths that will work and create a standing wave, but not just any wavelength, okay, will work. And that's the point, that you really got to get out of standing waves. And it's really easy to calculate the wavelengths that will work. All right, so let's kind of see pictures of this. This is out of your book. And so here's what I mean. Lambda 1, I told you it's twice the wavelength, 2L over 1, or sorry, twice the length of the string. In other words, what we have is we get half a wavelength in here. If I were to draw this wave on out, it would want to do this and then go down here. Of course it can't because it's at a boundary, but what we have is half of a wavelength will work because we get a node here and a node here. And so that'll work. Lambda 2, okay, that's where you, if you actually did the math, you would just get the L. You can see this is the wave where, again, we have nodes at the middle, but we're going to get or at the ends, and we're going to get a node in the middle, but we've got one full wavelength that will fit in here. Now that lambda 3, which was 2/3 over L, well, think about it. L is here, right? 2/3 of that would be 2 of these things. And you can see that's a complete wavelength, okay? So you're actually getting 1.5 wavelengths in here, but that works because we get nodes at the boundaries, all right? And then down here, we've got the 2L over 4, and that's half the length. And you can see we've got one wavelength here that's covering half the length of the string. And so we're actually able to get 2 full wavelengths in there, and that's a wavelength that will fit. Okay, and that's the whole point. We're trying to find what are the wavelengths that will fit in there so that we can have nodes at both ends. And so this lambda equation just helps us figure out what those possible wavelengths are. Now here's the thing. We can think about all of this in terms of frequencies too. We talk about, well, what wavelengths will fit? Well, the question really is, well, what frequencies will create the wavelengths that do fit? And so if I do that, then let's just think about it. Frequency is velocity over wavelength, right? Well, what that means is that the frequency for any m, okay, any wavelength, is just going to equal v divided by 2L divided by m, right? And so this would be the general way to calculate the frequency. I've just taken the velocity of the wave, which is always the same because the medium hasn't changed. And now I'm just putting in all the possible wavelengths that I could have in terms of whichever m value that I'm looking at. And if I do the math and wrangle that around, what I find is that the frequencies that will work are equal to m, which can be 1, 2, 3, 4, whatever, right, times v over 2L. And so what that means is that if we look at this lambda would be created by a frequency that is simply v over 2L. M is 1. If I put 1 in here, I just get v over 2L. And so this is the wavelength that will fit. This is the frequency that will actually create that wavelength. And we could put in our numbers and calculate an actual frequency. And it's going to give me a wavelength that's long enough that half the wave fits in between the two boundaries. And we can go down. The frequency that creates this wavelength would be twice this v over 2L. And hopefully you're seeing we're just getting multiples of this v over 2L, aren't we? F3, this is the frequency that would create this wavelength. This is the frequency that would give us 1.5 waves that fit in here and work. And then we could go on down and so on. So I want to look at this first one. This first frequency that gives us the half wavelength and the first overall wavelength that will fit. We call this the fundamental frequency. The thing I want you to realize is that every frequency that creates a standing wave is a multiple of the fundamental frequency. In other words, the frequencies that work are always whatever m value you're looking at, whether it was the 2 or the 4. If you want the frequency that works, you just take, say, if it was 4 times the fundamental frequency. So this fundamental frequency is really important. It kind of tells us, what's going to happen each time. In fact, the frequencies are always going to step up by a v over 2L each time, right? Because you can see that they're just multiples of that. Now, frequencies beyond the fundamental, we have a name for those. We call those harmonics. So this is the fundamental frequency right here for this wave on a string. This would be called the second harmonic, the third harmonic, the fourth harmonic. So when we talk about harmonics, we're just talking about what multiple of the fundamental frequency it is. If it's the third harmonic, it's 3 times the fundamental frequency, okay? And so this is kind of how it works. And I want you to see, again, what we're determining here is there are only specific frequencies that will actually create standing waves, and those specific frequencies lead to specific wavelengths. And the wavelengths are pretty cool, okay? Now, there's some things I want you to note. I'm pulling these straight out of your book because they're important. First of all, did you notice that m, whatever m we're looking at, is always the number of antinodes on the standing wave? I mean, come back over here. M was 1 for this one, right? How many antinodes do we see? We see 1, okay? M was 3 down here. How many antinodes do we see? 1, 2, 3. 4 down here. 1, 2, 3, 4. So your m value, whichever harmonic you're at frequency-wise, that's going to tell you how many antinodes are going to be set up on that standing wave, okay? The fundamental mode, be careful with this one, and this is important, has a wavelength that is twice the overall length of the string. It's not equal to the length of the string. Remember, this is not a full wave pattern. If it was the full wave pattern, we'd see it go from here and then stretch on out, but it doesn't. The wall stops it. So the wavelength of the fundamental is twice the length of the string, okay? And students do get that backwards sometimes. They think it's equal to the length of the string because it's the first one and it's fitting in there. Okay, the final thing is that the fundamental frequency is always the difference between consecutive frequencies, okay? In other words, you can always find the fundamental by taking the difference between, say, one frequency or one harmonic and the harmonic behind it. In other words, if we look at this, the difference in this one and this one, well, I've got 3V over 2L minus 2V over 2L. What's that going to give me? It's going to give me V over 2L, okay? So anytime I take a harmonic and subtract the frequency of the previous harmonic, okay, I'm going to get the fundamental out of that, okay? Just an interesting side note, if you play a stringed instrument like the guitar, you're always creating the fundamental frequency for the length of the string from, say, your finger to where it attaches on the guitar over the sound hole, okay? So, music is a wave phenomena. Stringed instruments are standing wave phenomena, and it's just all really cool, okay? So that's just the basics that I want you to see. Now, let's apply some of this information to a problem because I think you need to see it in action. Let's suppose we have a 2-meter long string and it's vibrating at its second harmonic frequency. Now, you're hearing second harmonic and you're already thinking, oh, 2 antinodes. Okay. It's got a maximum amplitude of 2 centimeters, and one end of the string is at x equals 0 centimeters. And it wants to know, well, what's the oscillation amplitude at 10, 20, 30, 40, and 50 centimeters? Okay, well, let's tackle this problem. Let's use our process that I started teaching you last year. Let's write down our knowns. So let's go through. Well, we know that we're at the second harmonic frequency, right? So we know that M is equal to 2. We also know that the maximum amplitude is 2 centimeters, right? And we know that the length is 2 meters right here. And what it's asking us to find is what's the amplitude at 10 centimeters. So on that standing wave, what's the maximum displacement of that medium at 10 centimeters, and then at 20 centimeters and so on, all the way up to 50 centimeters. Okay? Well, if we want to find an amplitude, that automatically tells us we're going to have to deal with the amplitude function. We need to figure out what that is. And of course, that function has the form, this A max, which is 2 times the amplitudes of the waves. We've got this maximum amplitude times the sine of KL. Or sorry, that should be X. That's a mistake. Do not write L in your notes. Write X right there, okay? So the amplitude function is A max times the sine of KX, okay? So if we can figure out K, then here's the thing. We can substitute that back into our amplitude function right here, and then we can actually solve for the value of A at any point. Well, so what we need is K. K is 2 pi over lambda. So what is the wavelength? Well, I need to draw a picture. There's a picture of the situation I'm at. I'm in the second harmonic. So that means if I were to draw my standing wave between the 2 boundaries, I have to have 2 antinodes. And so this is the picture that's going to work for that. And so, look at this. This is M equals 2, second harmonic. Now, what do you notice about the wavelength of the second harmonic? Well, it's just equal to the length of the string. It's going to be 2 meters, right? So if I use that, then I can find K using this equation. It's just going to be 2 pi over 2, which is pi radians per meter, right? Okay, now be aware, we're working meters here. That's a meter, and that's going to play into our equation up here, right? So let's take a look at this. A of x is going to equal 2 centimeters times the sine of pi x. That's what our amplitude function becomes. And so now what I'm going to do to find the oscillation amplitude at these various x's is I'm just going to substitute that into my equation down here and calculate it out. But now I need to be careful. This 2 centimeters is fine. It's out front. But this pi that we calculated is got meter terms in it. So if I'm going to use this equation, I need to turn my 10 centimeters into meters. I need to change my units. And so what I had to do for the first one was put in A of 0.1 meters. I had to put in 0.1, not 10. and that gave me 0.062 centimeters, right? So I just put it in and calculated it. I did the same thing for 20 centimeters, 0.2, and that's 1.2 centimeters. I did the same thing for 0.3, that's 1.6 centimeters. A of 0.4 is 1.9 centimeters, and A of 0.5 is 2 centimeters, okay? And so that makes sense because think about it. If this is 2 meters long, our wavelength is going to be 2 meters. And the distance out here to half a meter, so this would be 1 meter or 0 meters, half a meter, 1 meter, 1.5 meters, and then 2 meters. Well, at half a meter, we're right here. That's at our maximum amplitude. And you can see that we get out of our equation the 2 centimeters that we expected. And so that's kind of a problem with how you can work with this. And that's standing waves. So if you have any questions, touch base with me. I'll be happy to help. But you've kind of got the theory now of superposition, and we've applied it to a very specific situation, and that's the situation of standing waves.